Variable Gain Amplifier, LMH6505 from National Semiconductor. Welcome to the training module on National Semiconductor's Variable Gain Amplifier, the LMH6505. This training module overviews the LMH6505 Variable Gain Amplifier and discusses its key features and applications. The LMH6505 is a wideband, DC-coupled, voltage-controlled gain stage followed by a high-speed current feedback operational amplifier which can directly drive a low-impedance load. The gain adjustment is 80 dB for up to 10 MHz, which is accomplished by varying the gain control input voltage. Power consumption is 110 millivolts with a speed of 150 MHz and a gain control bandwidth of 100 MHz. Output referred DC offset voltage is less than 55 millivolts over the entire gain control voltage range. The output current feedback op-amp allows high-frequency, large signals with a slew rate of 1500 volts per microsecond and can also drive a heavy load current of 60 milliamps guaranteed. The LMH6505 combines a closed-loop input buffer, the X1 block, a voltage-controlled variable gain cell, the mult block, and an output amplifier, the CFA block. The input buffer is a transconductance stage whose gain is set by the gain setting resistor RG. The output amplifier is a current feedback op-amp and is configured as a transimpedance stage whose gain is set by and is equal to the feedback resistor RF. Maximum gain is set by external components and the gain can be reduced all the way to cutoff. The circuit describes a typical application. The input buffer is a transconductance stage whose gain is set by the gain setting resistor RG. The output amplifier is a current feedback op-amp and is configured as a transimpedance stage whose gain is set by and is equal to the feedback resistor RF. The maximum gain, AV max, of the LMH6505 is defined as the ratio K times RF over RG, where K is the gain multiplier, with a nominal value of 0.940. As the gain control input VG changes over its 0 to 2 volt range, the gain is adjusted over a range of about 80 dB relative to the maximum set gain. Maximum gain is set by external components, and the gain can be reduced all the way to cutoff. Although the LMH6505 is specified at AV max equal 9.4 volts per volt, the recommended AV max varies between 2 and 100. Higher gains are possible, but usually impractical due to output offsets, noise, and distortion. As the IRG max limit is approached with increasing input voltage or with lowering of RG, the device's harmonic distortion will increase. Changes in RF will have a dramatic effect on the small gain bandwidth. The output amplifier of the LMH6505 is a current feedback amplifier, a CFA, and its bandwidth is determined by RF. As with any CFA, doubling the feedback resistor will roughly cut the bandwidth of the device in half. The LMH6505 can be configured for use in a single supply environment. Doing so requires the following: bias pin 4 and RG to a virtual half supply somewhere close to the middle of the V+ and V- range. The other end of RG is tied to pin 3. Ensure that VG can be adjusted from 0 to 2 volts above the virtual half supply. Bias pin 2 to make sure that it stays within the range of 2 volts above V- to 2 volts below V+. This can be accomplished by either DC biasing the input and AC coupling the input signal, or, alternatively, by direct coupling if the output of the driving stage is also biased to half supply. Arranged this way, the LMH6505 will respond with the current flowing through RG. The gain control relationship will be similar to the split supply arrangement with VG measured with reference to pin 4. Gain accuracy is defined as the actual gain compared against the theoretical gain at a certain VG, the results of which are expressed in decibels. The max value would be the worst case difference between the actual gain and the theoretical gain for the entire population. Gain matching is the limit on gain variation at a certain VG expressed in decibels. The max value would be the worst case difference between the actual gain and the typical gain for the entire population. If high levels of gain are needed, gain partitioning should be considered. The LMH6624 is a low-noise, wide bandwidth voltage feedback amplifier. Setting R2 at 909 ohms and R1 at 100 ohms produces a gain of 20 decibels. Setting RF at 1000 ohms as recommended and RG at 50 ohms produces a gain of about 26 dB in the LMH6505. It is important to understand that when partitioning to obtain high levels of current, very small signal levels will drive the amplifiers to full-scale output. Through gain partitioning, the designer is provided with an opportunity to optimize the frequency response, noise, distortion, settling time, and loading effects of each amplifier to achieve improved overall performance. Offsets can be broken into two parts, an input referred term and an output referred term. These errors can be trimmed using the circuit in the figure. First, set VG to 0 volts and adjust the trim pot R4 to null the offset voltage at the output. This will eliminate the output stage offsets. Next, set VG to 2 volts and adjust the trim pot R1 to null the output voltage, offset voltage at the output. This will eliminate the input stage effects. Digitally variable gain control can be easily realized by driving the LMH6505 gain control input with a digital to analog converter. The diagram illustrates such an application. This circuit employs National Semiconductor's 8-bit DAC 0830, the LMC8101 MOS input op-amp, which is a rail-to-rail input-output op-amp, and the LMH6505 variable gain amplifier. With Vref set to 2 volts, the circuit provides up to 80 dB of gain control in 256 steps with up to 0.05% full-scale resolution. The maximum gain of this circuit is 20 dB. Here are some considerations to avoid problems and to get the best performance. In automatic gain control applications, the control loop forces the LMH6505 to have a fixed output amplitude. The input amplitude will vary over a wide range, and this can be the issue that limits dynamic range. The AGC circuit shown will correct a 6 dB input amplitude step in 10 nanoseconds. The current includes a 2 op-amp precision rectifier amplifier detector, U1 and U2, and integrator U3 to provide high loop gain at low frequencies. The output amplitude is set by R9. The following are some suggestions for building fast AGC loops. Precision rectifiers work best with large output signals. Accuracy is improved by blocking DC offsets. A fast-settling AGC needs additional filtering beyond the integrator stage to block signal frequencies. This is provided in the figure by a simple RC filter, R10 and C3. Better distortion performance can be achieved with a more complex filter. These filters should be scaled with the input signal frequency.